Okay, so I want to just for a moment have a little talk about this same situation. What if so given this setup here, I just wanted to ask the question, what if I were to, let's see. What if I gave you the picture like this? She says it's the same. You don't have an issue with that. She doesn't have an issue with that. The numbers are given. Crunch closer together. What about the fact that the amount of sand that we need is always more than the amount of cement that we need, but I'm making the sand bar shorter than the cement bar? Shrugging your shoulders, like, it's okay. She says it's okay. Yeah?
It's not okay because the units are the same, so that each should be like in a ratio.
Okay, so he's saying because they're both measuring in cubic yards, you want them to line up. You want 1 cubic yard on one bar to be the same as 1 cubic yard on the other.
I mean like how it was before.
How it was before. So like that's okay.
Yeah.
What about that? Would that be okay? How about if I made them the same length and move those labels? Yeah.
Wouldn't it be okay because you're specifying the scale of how much per tick mark it is. So as long as there's an equal amount of tick marks to make the ratio equal, then it should be fine.
Yeah. So yeah.
Aren't the two scales correlated? So if you mess up the range on one, wouldn't that have to correlate to altering the range to match that first bar?
Okay.
So wouldn't it make them both?
Other comments? Yeah.
I don't think it matters too much, just like on a graph, you have just two different lines, you can run whatever you want as long as
You can change the scales on a graph.
Exactly.
You could like zoom way out or in on one of the scales, and the other could be different. Even it could be the same unit, even,
Yes.
and you could zoom in and out on one axis. Good conversation. How about in the white shirt?
Yeah, I think it's like it would be cool if they were exactly even, because then you get like it's like the perfect mix, you know. So it's kind of like scaled proportionately. What you want.
All right, so they're exactly even. That means I put the 7.5 right above the 3.
Yeah.
Yeah? And then do that. How about that?
It doesn't work if the whole point of this is to help you visualize values. If you're making them the same, then what's the point of doing that?
I think that's Harlow's way of visualizing that they're proportional.
Yeah.
These are all, so this is what I wanted to wrestle with. I wanted us to kind of struggle with this. And so basically, when I draw this red bar and I put this 3 here, I'm committing to 3 units on that bar. So if I come over here, how many cubic yards of cement is that? 1.5, right? That can't be 0.5 or 2 or 2.9. With that 3 there, I'm committed to a certain scale on the red bar. Even though the units are the same, a measurement on the blue bar, I can still have a different scale. So, but once I choose the scale on that blue bar, what's that? That's 15. That's got to be 15. Okay. So in your, in the examples we did in class and maybe in the homework, it's kind of like we were always seeing kind of the same 2 length bars, right? But really the relative actual image that you see is okay. It can change, stretch, or compress as long as on a particular bar you have a consistent scale, and then you know what corresponds. So in this case, we have our 7.5 corresponding to 3, and this value C corresponding to S, and maybe 9 corresponds to, what would 9 correspond to? 22.5. So there is nothing magic about maybe the same diagram that we always started with, where the bottom bar was shorter, and maybe 1/3 as short. We kind of saw a lot of those. There's nothing magic about that. We were just starting with 2 bars, so they could be the same length. The top one could be shorter, bottom one could be shorter. Doesn't matter as long as you're consistent on the individual scales and consistent on your correspondence between them. Are we good? Okay. That being said, this exercise is going to have a matching scale for the 2 bars. Can we adjust okay like that? So now in this exercise, no, that's not true. That's not true. You don't need it. So just ignore what I just said. Okay. So what I'm going to do here is I'm going to extend the red bar to here. Oh, sorry. That's okay. We'll leave it up there. Okay, so I'm going to extend the red bar to there. And I'm going to then, when I extend the red bar to there, the blue bar is going to change, and you're going to predict where the blue bar will extend to using these letters that I've given you. Okay? So you can kind of see a grid there. You don't need to try to count the grid. It's just more about approximation to estimation based on the idea, okay? Based on what we've been talking about. So this is not about counting squares, okay? It's about the idea of relative size, okay? So I'm going to extend the red bar up to that black mark, and you're going to have a short conversation with the person next to you. Where do you think the blue bar is going to extend to? Go. Okay. So somebody knew. Where did you think the blue bar was going to end up? Somebody knew, and why? Gold trigger. I'm going to learn your names, by the way.
About double.
So tell me. So what do you think?
G or H?
G or H. So exactly double, less than double, more than double.
Little more than double.
Little more than double. Want to do it? Here we go. Ready? It's really touchy. Sorry. There we go. It's really hard to do on the trackpad. How do you do? Okay, so what kind of reasoning did he use to answer that question? He said a little more than double. What kind of reasoning did he use? We talked about some different kinds of reasoning. Yes, sir. Yeah.
Well, the second one would be still the initial length that we wanted to extend it.
Yeah.
It was a little more than half of the red bar.
Okay.
So then the blue bar and the scaling factor would double as well.
Okay, so she said scaling factor, right? So he's thinking it's scaling up by a little more than double, therefore the blue one is going to scale up by a little more than double. Okay? So that was the kind of reasoning he used. So I'm going to go back to where it was, maybe. Then, had it. I had it. There it is. Okay, and now I'm going to tell you that this is 4. And this is 9, and this is 200. I want you to do the same exercise, but put some mathematics behind it. Same exercise, but put some mathematics behind it. Go. So what will the quantity or the value of the represented by the blue bar be when I extend the red bar to mean 9? 450. And so what was your thinking to get that? Tell me what your reasoning was.
I looked at it how many times we, so to say, multiplied the red bar, which is 2.25.
Okay.
And then I multiplied it by 2.
So is it 2.25?
Yes.
So what kind of reasoning is that? I'm hearing scaling. Is it scaling reasoning? Yep. If the red bar gets scaled up by 225, then? And so you said the final result was? 450. Scaling reasoning. Scale up one by 2.25, you scale up the other by 2.25. Did anyone reason it a different way? Christian?
Yeah, I took 200 and I divided it by 4 to see how many units each one had.
Okay.
1 to 1. And so 1 unit was 50 units of the top one, so 50 times 9 units, which is what you increase the bottom one by, is 400.
All right, so you looked at the 4 and you said, oh, to get 200 from 4, you multiply by 50. So therefore, when the red bar gets to 9, to get the corresponding value of the blue bar, multiply by 50. Scaling reasoning? Scaling reasoning? No, that's not scaling, remember? What is this? Constant multiple. Constant multiple is the reasoning that takes you from one quantity, a value of one quantity, times a constant multiple to give you the corresponding value of the other quantity. So that's what the times 50 would be doing. Both are legitimate for this, and both work to show us that when red is 9, blue is 450. Anybody have a question? So yeah.
So in the first process, I guess 2.25 would be the constant multiple, right?
Scaling factor.
Scaling factor.
Scaling factor is how you resize a quantity. And when you have the two quantities changing together, if you resize one by the scaling factor, the other gets resized by the same scaling factor.
But wouldn't 50, doesn't 50 do the same?
No, it's not scaling because there could be two different quantities. So that's why we call it a constant multiple. You start with a certain value of a one quantity. The constant multiple gives you the corresponding value of a different quantity.
Okay.
Scaling is about resizing a quantity,
Okay.
regardless of another quantity. Constant multiple is about giving us a corresponding value of a different quantity. Yeah. Other questions? All right, so I'm going to change it up here. If we can read that. Okay, so I'm going to extend the red bar to, let's make it fun. Here. I'm going to extend the red bar to there. Where's the blue bar going to end up? And I want you to practice both kinds of reasoning when you do this. So where's the blue bar going to, the length of the blue bar? What will it be when I extend the red bar to this point? And practice figuring that out using both kinds of reasoning, both scaling and constant multiple. Have a conversation. Go. long way over, and you don't have numbers, so this is not exact science, okay? But it's about the reasoning. That's the more important thing than knowing exactly, trying to make a really good prediction, okay? So, somebody new. Yes, sir.
The red bar looks like it's going to go roughly like 4.5 times itself.
Okay.
The black line. So if you move the blue bar 4.5-ish times, it's going to end up at about F or G.
Okay. So, what kind of reasoning was that? You said red will get scaled by 4.5, therefore blue will get scaled by 4.5. So hopefully you practice the other kind too. Somebody new. For the other kind of reasoning. Yes, ma'am.
The blue bar is like about a third of the red bar.
Okay.
So if the red bar was extended all the way out, then the blue bar would be 1/3 of that size.
Is that the other kind of reasoning?
Yes.
Okay. So, yes, exactly. So let's see. So what letter are you predicting? What letter? You predict F? Is that what you said too?
Yeah.
Anyone say a different letter? Are we agreeing on F?
I'll say G.
G?
G, no, FG.
FG?
I'll say
Too late.
nailed it.
Okay, so actually, in actuality, the blue bar is 1/4, exactly 1/4 of the length of the red bar. Okay, so it's 1/4. So the relative size of the blue bar to the red bar is 0.25, or 1/4. Okay, it's 1/4 as long. Okay. Good. So let's get rid of these. Did you hear that? Listen. Shh. All right. Easily entertained. Okay. So what I'm going to do next is related to your homework. Oh, no. So now we've really been talking about these bars very statically, right? We look at one situation, we analyze it, and then we compare it to another situation and analyze it. But really, what this course is about, I think, did I say this course is about quantities? Did we say that? So let's be a little more specific. This course, it's about quantities, but it's specifically about changing quantities, okay? And even more specifically, how two quantities change together. This is really what calculus, the science of calculus is. It's modeling mathematically how two quantities change together, all right? And so we want to kind of transition to a more fluid or dynamic way of thinking about these. So I can turn this on. No. This hasn't been working lately. I can just move it manually, I think. There we go. Okay, so imagine that the red bar increases, and as the red bar is increasing, of course the blue bar is increasing, but how is the blue bar increasing as the red bar, the value of the quantity represented by the red bar, increases? Yeah, so the relative size is maintained. So as the value represented by the red bar increases, the blue bar is always maintaining that 1/4 relative size. So now we're starting to think about how two quantities change together. And this is a very specific way that two quantities can change together. Relative size is maintained. Relative size is maintained. In this case, the relative size of the blue bar is always 1/4 of that of the red bar. So in your homework, toward the end of your homework, you had it told you, it said, we're going to take that blue bar and we're going to flip it and put it on the end of the red bar. So the start of the blue bar always is attached to, or right there, no matter where the red bar is, that will always be the start of the blue bar. And then it will be pointing up, vertically. So I'm going to try to get the animation to work, because that's really, and as I'm trying to get the animation to work. So if I were to do that, and I got the animation just to run fluidly without me dragging it, what would you see? What would you see? So have a conversation with the person next to you. What would you see if we take that blue bar, flip it, and plant it on the end of the red bar, and then extend the red bar? Extend the red bar. What would you see? Okay? Talk about it. Little slow though. Yeah, I got it to work. Okay, so I'm going to have the same, the relative size of blue to red will still be maintained, but the blue bar is now going to be parked vertically on top of the end of the red bar. What are you going to see?
Oh, I was just actually going to ask, can you do this on your graphing calculator?
Yeah, this is a graphing calculator program that I've created to make this visual. So when I do visuals all semester, they're all built with graphing calculator. Okay, and sometime next week we're going to start you're going to start learning the basics of it and start using it too. Okay, but yeah, so when I'm doing these, whenever you see these visuals, these animations, it's using graphing calculator. So what are we going to see when we flip the blue bar up? You want to answer that now? Yeah.
Yeah, so we're going to see the same thing, that it's going to go up still by 1/4, but it's going to extend vertically.
Okay. What's that? Like a capital L but shorter. Okay. What's that? It'll make an XY plane. Other, yeah.
The end of the blue line trace a diagonal.
The end of the blue line will trace a diagonal line. What do you think? Let's do it. So what is this about? What is this about besides awesomeness? Sorry. Triangles. What are we? Graphs. Cosine, sine, and tangent.
Related rates.
Related rates. What's that?
I was going to say like congruent triangles.
Congruent triangles. Scaling. Calculators. Okay. Everyone seen this before? What is it? It's the vapor trail from a plane, right? There's a couple, right? There's a couple. I don't want to be on this plane. Yeah, sure. What does, okay, so when you look at, say, the one on the left, so what does the vapor trail represent? What is it showing you? What is it representing? Direction.
Trajectory path.
What's that?
Trajectory path.
Trajectory path? That sounds like in the future.
Well, the path it took.
Yeah, okay, the path it took.
Distance relative to time.
When you look at that, it doesn't tell you anything about time. It's showing you what about the plane? Showing you what about the plane? Where it's been, right? It's just showing you all the places that it's been. So what if I took our bar diagram and I put a plane on it, the top of the bar. And then we turn the vapor trail on. What would it show us? But what, so in the spirit of a vapor trail, what is the vapor trail showing us? No, you're looking way too far into it. No, just where that top of that blue bar has been, right? That's all it is. Where the top of the blue bar has been. Okay? And so what are we forming here by the vapor trail? Oh no, that was not what I wanted to do. Everything's okay though. This is what I wanted to do. Okay, we're forming a graph, right? So by looking at every place that plane has been, the vapor trail, we're forming a graph. So I'm just going to pause this here. So suppose this is x equals 7.719. It's really hard to write when you haven't done it in a while. Okay. 7 point. Okay, so say x is 7.719. Okay? So without a calculator, can you represent what is, so that's the length of the red bar is now our x coordinate, the length of the red bar. So what is the length of the blue bar? Or in other words, what's the y coordinate? So if we got 7.719, no calculators, no mental math, represent the value of the y coordinates, or the length of the blue bar. 1/4 of that, right? So last year you're thinking that. One-fourth of that.
And 1/4 says the bar of 1/4.
Right, we said that blue always maintains a relative size of 1/4 to the red, or the value of, now we're talking about the value of y maintains this relative value of 1/4 to whatever x is. So then that vapor trail, in light of this conversation that we're having, so we'll go back, here's they say here. So there's the top of the blue bar, or where the plane is right now, gives us another point, and that point is 4,1. So what do we get when we take every possible point, given an x value? We get this line, right? We get this line. When you look at that line, so when you see that line right there, how many points are you looking at? Not 2. I've highlighted 2. I've highlighted 2 points. So when you look at that graph, that is a collection of an infinite number of points. It's just a lot easier to draw it that way than to show the points. But that's what it's really about, is about a collection of points. Okay? So it's, in less than a second we can draw this line. But it's not a stick, it's not a wire, right, that you move around and bend. It's a collection of points. And each one of those points is a correspondence of 2 values. A value of one quantity and the corresponding value of another quantity. Okay? So this is how we want to think about a graph kind of emerging, right? Emerging as x increases. What corresponding values of y do we get for each value of x? All those points together make the graph. Okay? So it's about how the 2 quantities are related to one another, and then each point gives us one of those correspondences. All the correspondences represented by the graph. Okay, so let's suppose that. Let's put some actual quantities on this. X equals, so let me just, so here's what you draw, here's what you see in the book, see online, here's what you think. Here's what you think. That's what you think when you see a graph. Does that make sense? And then you know that each one of those points is the value of one quantity taken together with the value of the other quantity represented on the vertical axis. Okay, so let's put some. Right, so our labels here. Can't really see that too well. No, we're not ready for that. Let's put some actual real world stuff on this. So let's let x be is the volume of water in a test tube in milliliters. And y is the height of the water in the test tube in centimeters. So I'll turn the plane. So in light of that, so in light of this, now I've defined these quantities x and y, what is the graph showing or revealing? Now, just thinking about that x is this volume and y is this height as I've defined them. What is the graph showing? And then maybe talk about what are individual points showing. Go. So when we say y in terms of x, what we mean is we want something that will give us y's if we know x, right? So we want something that gives us what y is if we know what x is. So we need an expression of x's that will tell us, for a given x, what the corresponding y will be. And hopefully we all got that. What is it? 0.25x or 1/4 x. Okay, so what you're going to read about and answer some reflection questions is so this is a formula, but we also want to think about this as what we call a function. We could start off defining a function. So when you see this right here, this is what we call the function definition. We're defining this function. Okay, and so let's break down the meaning of this. In the definition of this function, f is the name. So I'm going to name that function this function f. X is input, or you can think of that as, our given value, or input value. So what quantity is the input in this function? What quantity is the input in this function? Volume of water in the test tube. That's what the input into this function is. And then when we come down here and I write f of, say, 2.9, this whole expression this whole thing stands for what? Output. So the definition is telling us, the definition tells us how to get outputs, or what. So in the definition, that f of x is, in general, here's the output. So this is output. This is how we're going to get output. We're going to take the input and divide by 4, or multiply by 0.25, and that will give us the corresponding output. So this defines it. Now, after we define it, we use this expression here. So this is the output, or what quantity is that then? This is the height of water in centimeters, but we can do better than that. When? When the volume is 2.9 milliliters. So that whole thing together, f of 2.9, means the height of the water in centimeters when the volume is 2.9 milliliters.
That's when it's divided by 4, right?
What's that?
When 2.9 is divided by 4, then that's no.
All right, so when volume, sorry, just got to get an answer. Volume is 2.9 milliliters. So we want to be, so we can use this notation and talk about without calculating that volume. See, this is where maybe this is different from how you've done function notation past. How many people, when you looked at that, you just immediately thought, oh, I'm going to calculate something? Yeah? So, but it stands for something on its own, and we want to use that kind of language. So we can just write that. We don't have to calculate anything, and we know what it means. It's the output of this function when the input is 2.9. Or it's the height of water in centimeters when the volume is 2.9 milliliters. Okay, and we'll definitely be getting to that. Okay, so you will have a reading and some reflection based on this function idea. This is a very quick introduction of a reading. Get out a note card.